Alright guys, in 2.4 we're going to be practicing with some algebraic proofs. So we're essentially going to be solving equations, but we're going to be doing it in a format which you're going to see a little bit more when we move on to the unit and get into two-column proofs. So before we do that, we need to discuss some properties that we're going to use as we're solving these equations and as we're constructing these two-column proofs. It'll make more sense when we get to some examples on the back, but the addition property of equality just says if A is equal to B, then A plus C is equal to B plus C. So if we were to see like an algebraic example of that, what we did to this equation was we added something to both sides. We added C to both sides. So if we were using a more algebraic example, we would say that x minus 3 is equal to 5. Well, in order for us to solve for x, we're going to add 3 on both sides to give us x is equal to 8. So with the addition property of equality, you guys have to remember that you're adding to both sides. Add to both sides of the equation. It's not just happening on one side, but it's got to be happening on both sides of the equation. And that's actually going to be the case for subtraction, multiplication, and division. Everything's going to be happening on either side of the equation, or on either side of the equal sign. So subtraction, if A is equal to B, then A minus C is equal to B minus C. So again, our example, this time we're going to say y plus 7 is equal to 9. In order for us to solve for y, we're going to subtract on both sides to give us y is equal to 2. So again, we're going to subtract on both sides of the equation. If we are doing that, then we are using the subtraction property of equality. Next one is the multiplication property of equality. So if A is equal to B, then A times C is equal to B times C. Here our example would be, let's say we have x divided by 6 is equal to 2. Well, in order for us to get the x off of the denominator, we're going to multiply it on both sides of the equation. So what this is going to turn into is going to turn into x is equal to 12. And again, it's happening on both sides of the equation. So I'm just going to kind of put some little quotes here. We're multiplying on both sides of the equation just like we did when we were adding and subtracting. Division property. So if A is equal to B, then A divided by C is equal to B divided by C. Our example here is going to look like 4x equals 20. So if we wanted to solve for x, we're going to divide by 4 on both sides of the equation so that x is equal to 5. Again, we're going to divide on both sides of the equation. So these first 4 properties of equality are happening on either side of that equal sign. Okay, our reflexive property of equality is pretty much saying that something is equal or congruent to itself. So a little symbol would be that A is equal to A. It could also look something like AB, segment AB is congruent to segment AB. And when we get into some geometric proofs, this will start to make more sense, and you'll see it in geometry a little bit more versus the algebraic proofs. But we could say that angle B is congruent to angle B. So again, the reflexive property is just saying that something is equal or congruent to itself. Again, we'll see it more with the geometric ones versus the algebraic proofs, but something good to go ahead and introduce to you. The symmetric property of equality, so if A is equal to B, then B is equal to A. So here you're just kind of like switching the order. They mean the same thing, but we're just ordering a little bit differently. So we're kind of flipping what we have on either side of the equal sign. So if we had another example here, let's say that we said segment CD is equal to 5 plus segment AM, then you could also order that to say 5 plus AM is equal to CD. Again, we just kind of flipped what we had on both sides. So we would just flip the sides. Sometimes we will have to use this one with these with our algebraic proofs if we're trying to prove that x equals a number, but as we're solving everything, it turns out to say a number equals x, then we would use the symmetric property to flip it so that we're ultimately finishing our proof with exactly the statement that we're supposed to end with. And when we do an example, that'll make more sense. So transitive property of equality. So if A is equal to B and B is equal to C, then we're able to conclude that A is equal to C. So because A and C are both equal to the same thing, B, we're able to conclude that A is equal to C. So if we come over here for another example, let's say if A is equal to 5 and 5 is equal to C, then A is equal to C because they're both equal to that 5. They're both equal to the same thing. Substitution property. So if A equals B, then B can be substituted for A. Can be substituted for A in any expression containing A. So let's say we have an example here. Given x is equal to 6 and 2x, so we're given both of those pieces, we can plug 6 in for x to give us 12 as our answer. So we really just plug into the equation. Then the last one we have is the distributive property. So if we have A times B plus C, then when we use that distributive property, that's going to look like AB plus AC. When you multiply A and B together, you get AB. Then you're going to add what we get when we multiply A and C together. The other example down here would be using subtraction. So if we had B minus C, then what that would come out to look like would be AB minus AC. Again, you're just distributing that A to both terms. If we wanted an algebraic example, we could have 5 times x minus 3. When we go ahead and distribute, that is the equivalent to 5x minus 15. Before we go ahead and do our examples, I went ahead and filled this part out for you guys, so if you need to pause the video so that you can get caught up, you can. But it's essentially the same thing that we kind of did on the front. Here you guys have your properties of equality for length and measure, in particular for our segment length as well as our angle measure. Not going to see this as much with our algebraic proofs, but you will see it when we get into our geometric proofs. So not a bad idea to go ahead and introduce it to you if you guys want to go ahead and pause the video and get caught up with those. Okay, now moving on to our first algebraic example. And as you guys can see, I've gone ahead and set up something called a 2-column proof. On the left, we always put a statement, and on the right is always the reason for that statement. So what we always start with, no matter if it's an algebraic proof or a geometric proof, we always start off with the given information. So we're going to write it exactly as we see it here. So our given information is this equation right here, which is negative 6 equals 3x minus our x plus 4. And again, the reason for that is given. I would be very organized when you guys are writing your proofs, just so that you can kind of see which statement correlates with what reason and vice versa. So what we're ultimately trying to do is we're ultimately trying to prove that x is equal to negative 1. So all we're doing is we're trying to solve for x. So our first step in probably doing that, and again, sometimes the order of our steps might differ from each other, but we're still going to end up with that same result. What's happening in the middle doesn't necessarily always have to be in the same order, but we do want to make sure that we're following the right steps to get to the same end result. So what I'm going to do first in my solving for x is I'm going to go ahead and I'm going to distribute this negative sign to my x as well as to this 4. So when I do that, you guys are actually going to write what it looks like after you've done it. So what it will look like after we've done it is you're going to have 3x. Again, we're going to make this a minus x, and this is going to be a minus 4. So minus x minus 4. Our reason for being able to make that statement was the distributive property of equality. You guys don't have to write all that out if you don't want to, okay? So next step is I would, if I were you guys, go ahead and combine like terms here. And I know that that wasn't a reason in the front, but that is going to be a reason that we're going to be able to use in these algebraic proofs. So after I've combined like terms, let's write what that's going to look like. So you're still going to have your negative 6 is equal to, well, 3x minus x is 2x minus 4. Okay, again, the reason that we were able to write that statement is by we combined like terms. Okay, next step in trying to solve for x is I'm going to go ahead, because I already have x on this side, I'm going to move that 4 over to this side here using the addition property of equality. So when we add 4 on both sides, you're going to write what that looks like in step number 4. So when we add 4 over here, you're going to have negative 2 is equal to 2x. Again, that's because we added the 4 on both sides, and when we're adding something on both sides, we're using that addition property of equality. We are almost there. So next step in getting x by itself is let's divide by 2 on both sides. So when we divide by 2 on both sides, negative 2 divided by 2 is going to leave us with a negative 1 equals x. And again, this was because we divided by 2 on both sides. So this is the division property of equality. That's our reason for being able to write this statement here. Lastly, we have solved for x, but we need our final statement to match exactly what our prove statement is. So given is always first, prove is always last. So we want it to look exactly like it does up here. So we're going to have to use that symmetric property to switch what that looks like here. So we're going to make statement number 6 as x equals negative 1, and we were able to make that switch because we used that symmetric property of equality. And there we have proven that x is equal to negative 1. Here is our reason. So in y'all's proofs, guys, you're not really showing your work. You're just kind of writing out what the next step is going to look like. And we're putting our reasoning for being able to write that step over on the right. So for the sake of time, I went ahead and worked out this second example for you. So if we want to, we obviously start off with that given information, which is our equation that we're starting off with. We want to get rid of that 10 in the denominator, so we would multiply both sides by 10, and we would end up with that 2x minus 5 equals 30, okay? Because when we multiply by 10 on both sides, over on the left, it's going to get rid of that 10 that's in the denominator. Again, our reason for being able to write this statement was we used the multiplication property of equality because we multiplied both sides by 10. Next step in trying to solve for x, which is what we're doing, is I would go ahead and add that 5 on both sides of the equation. So when we do that, you're going to next have 2x is equal to 35. So again, we added on both sides of the equation, so we use that addition property of equality. And then lastly, to get x by itself, we're going to divide by 2. So when we divide by 2 on both sides, you get x is equal to 17.5. And again, we use the division property of equality because we divided by 2 on both sides.